right, let's get to it. Starting a new video today. We're going to start looking at speed density and what it is, how it works. So what is speed density? Speed density is a way of modeling airflow and corresponding fuel based on a couple of factors. One factor we have is engine RPM. And the other factor we have is we know air. And we know it in terms of, this is where it gets exciting. I know air pressure, barometric, and I know air pressure in the manifold, otherwise known as manifold air pressure. And so if I say this is 101, whoops, excuse me, ignore that. If I say the barometric pressure is 101 kilopascals, which is the unit we're going to use, I know that the maximum possible manifold air pressure in a naturally aspirated engine can only be 101 kPa. And so from 0 kPa, which would be an astonishing amount of vacuum, through 101 is the range my vehicle is going to operate in. And if I go back up here to RPM, I can start creating a grid where for all the pressures and all the various RPMs, I have cells. And in each one of these cells, I know what is referred to as the volumetric efficiency. What is volumetric efficiency? I'm so glad you asked. VE is the amount of air inside the cylinder that is optimally efficient for power production under these certain circumstances. It is usually between 0 through 100 in percent in modeling terms. And it has, of course, a corresponding fuel target to go with the volumetric efficiency. So for example, I could be in a cell. Let's say I'm medium RPM, medium pressure. So I'm in here. And I know that in that cell, for tuning, I know, thank you, you're helping. Okay. For that cell, for tuning, I may say it is 0.55 for the VE, or 55%. And with that, I want to have, how much fuel would I need? Do you know? We'll call it Y. Oh, that's terrible. It's ugly. Not that it matters. It's a whiteboard exercise. Y fuel. Right? And you learn later on that this is actually broken out into two factors as well. There's the fuel I direct inject and the fuel I port inject. And port injection, you can send massive puddles of fuel into the system to be made available. And the direct injection, though, is the injectors under high pressure. That is, the superfine mist. So the two together, I think normally you want to see that your port injection is no more than 10% of an overall fuel load. Don't quote me on this. And maybe the direct is supposed to be about 90, because that's efficient going right in the cylinders. If you start going lean, that PI can go up, but that's to bail you out. It's not a good situation, but I digress. Okay, so pausing one moment. Okay, so we know now that unlike a math curve, which is on those 2 dimensions, I now have a model with pressure in kilopascals on one side and RPM up here. And I have my individual cells, right? And for each and every one of those cells, I can monitor trims. Because the ECU on the 4th gen Coyotes and the S650s allows us to look at trims through the entire power band, low throttle, partial throttle, and wide open throttle. So it becomes easy to do a bass tune under idle, low power, and partial throttle, all with trims. And it turns out we can do watt, but watt is hard to get a lot of data. And so we do, in fact, also look at not only trims when we do watt, but we go back to the classic lambda or EQ error. And so this is a case where under watt, I'm commanding, 0.84 lambda, which is pretty rich. I'm getting 0.86, which is leaner than I would like. That's a 0.2 error, right? We would get a percentage. It wouldn't be 0.2, it would be something else. So like 5%, right? And it's 5% lean. Sorry, that's ugly as hell. But we're not going to get into that quite yet, right? We're going to stick in the bread and butter, idle, low power, and partial. We're going to look at trims, and you will see this as we set up a data log with filters. This one might be 4% off. This one might be -2. This one might be 3, 1, 0, 1, 2, -1. Right? This one's 5. This one's way off at 7. This one's way off at 8. Right? You're going to start to see those populate. And so we can then take that, layer it onto the model, and do an overall calibration. All right, weird bees. Okay, where we true up that table. Now there's 2 wild cards in this situation. Number 1 is the intake manifold runner control, or the IMRC. The IMRC is a little device that sits on the back of the intake manifold. It uses something like a phaser, or whatever you call it, the phase actuator, to move it into either a high or low state. Okay? These 3 see it in a low state, which is monitored as a voltage. And you will see that under 2 volts in that low state, the IMRC is open, and it behaves differently than in a high state where the voltage is greater than 3.0 volts. The high state corresponds to wide open. Do a little one of those. Okay, what good is that, you ask? So glad you asked. 2 is, remember I have a whole video. Do you remember the video on VCT and the mapped points? Do you remember? So, this is our table. There's a catch. This is for mapped point, we'll say 0. There is another table, mapped point 1, which will have a different grid. Isn't that exciting? And so if I have 26 mapped points, is it true that I then have 26 VE tables? Bet your ass it's true. In fact, it's 25. And they're broken into 0 through 9 is the low state of the IMRC. And 10 through 19 is the high state of the IMRC. And then 20 through 25 are for watt, or power. Okay? That's why that matters. And it so turns out that there's a little magic trick we can do where you find out that mapped point 1 corresponds and is tied to and has a relationship with mapped point 11. They are in fact identical. And map point 11 is the high state of map point 1, which is in a low state. And if we log efficiently, we can actually tune 2 mapped point tables at the same time if we filter on this voltage state. And you're going to see what that means when I go to the software. But that is what we are up against. So, we're not going to tackle all this in one video. There's too much going on. This is going to be video number 1. The next thing I'm going to show you are the filters I set up as I do logging. And then we're actually going to run a log on my car as it sits now, because I just layered in the Dark Horse torque limiters, which basically means by taking a GT tune file and adding in the Dark Horse torque control, along with a few other small goodies, you can essentially turn a Mustang GT into a Dark Horse. Okay? And while we do that, of course, anytime we make a change like that, we're going to want to log, make sure we don't have knock, make sure that everything's running right. And the big thing, of course, is making sure that we're not battling the torque monster, which is going to be a whole other video coming up. But that's the essence of speed density. So let's get to it. All right, so getting back into it. Here is my tuning file. You can see where I'm making some changes in torque. If I come back to airflow and I go to my speed density, okay, here are all the different speed density tables. This gets pretty exciting because there is 3 that we're interested in: offset, quadratic term, and slope. And so it's important to understand that speed density is mapped with these 3 different components of an equation to create what is essentially a large 3-dimensional contoured shape. And like a math curve, that shape should be pretty smooth. These elements working together will help set up that formula for what it is. Okay. So these are values here. Oh, not air mass values. What are you looking at? Let me close that. Show me offset, map point. Oh, okay. Guess I was right. So there's air mass. Let's see here. It corresponds to RPM and then what the air charge is. Right? It's pretty peculiar. There's the quadratic term. Okay. So coupled with those are these numbers here. And adding in as well is the slope with values here across the RPM. Okay. If you're confused, You goddamn well should be, right? Anybody would be, right? It would be hellacious to work with these and calibrate them in that state, right? So the truth is, we don't. We use, thank you HP tuners, we use the speed density calculator. And here it is in all its glory. I did a sneak preview previously. Split that into two here, right? And now you can see, like I was drawing on the whiteboard, we have a chart here which has kilopascals down one side. You see it goes from that 0 state up to possible 108. That would be very high pressure. That would be like sea level with a storm coming. That's pretty high. And of course, this would be like the vacuum of space up here, right? It's theoretical. It doesn't really exist. And then we have across here the RPM. And now looky, how about this? 0.02, which would be a 2.9% fill on a cylinder. The volumetric efficiency for power here would be 2.9%. As I go up to my bigger RPMs and I go to my bigger pressure, so let's say we have a wide open throttle, 93, and we're passing the 4,500 point, right? Here, I would expect that cylinder to be filled with 75% of air for optimal efficiency. That's what the computer knows it should be. That's how much air should be in there at that time. And it does a calculation and delivers the corresponding fuel based on that value. And you can see over here we have a graphed shape, and that we can manipulate this shape with a number of means. Right now I'm spinning it just with my right mouse button. Any one of these, though, we have the same relationship where I can see which cell I am on the table. And if I do something like move that, right, I can start drawing and shaping my table, sculpting it, all sorts of things. That actually becomes critically important in the GM world, right? Because the VVE table there is integrated into one larger table. Here in the Ford world, we get to see over here, look, all of our various mapped points. And so if I go to mapped point 10, this is the high state for the table 0 I was looking at. You can see the shape changes a little bit, okay? And so the name of the game is going to be to isolate these tables with our tune, which we're going to look at in the next series, right? But this series, just want to highlight this is what's going on, right? And I can go through any of these and I can start seeing these shapes change. I can see too that in some of these there's these weird spikes, and these can give you fits later on. Because the last thing I'll show you before we go to that, actually no, I'm going to keep it a secret. Don't worry about it. Going over here to our log, however, you can see now that I have a number of different histograms set up. These were the ones we were using for the mass airflow, and now these are the ones we're going to be looking at speed density with, right? And these are as well, but they're going to come later. So if I go to my layout, the first one I've set up here is something called aggregate trims. And what have I done here? Well, first of all, remember I said that we are going to be calibrating against trims. Trims are great. They're easy. They're intuitive. If I'm 5% lean, I know I bumped that cell up 5%. Next time when I come back, I'm only 1% lean, hopefully, right? And we just keep ripping through all the cells to get that. Okay, so we're still going to be looking at, as a parameter, the LTFT trims, like we were for mass airflow. And we are going to use bank separated, the aggregated value. So that's how I got that. I opened it, went to maths, the fuel trims, selected bank separated. I'm still going to have 2 decimals. And I'm not going to filter on it right now. I'm going to leave it raw because it gives me a sense of what I'm looking at. And I'm going to have 10 cell hits required because I want to filter out some of the junk data. I still have my scale of -15 to 15 for showing colors on my, if I'm lean or if I'm rich. And then we come to the good stuff down here. So for the column, and I'm going to come back up here. The column is our, or it's these. Column is the RPM, right? This is one column. this is the next, this is the next, this is the next. So for my columns, I know I need to have RPM is what I'm logging, and it needs to have, and this is really important, prick your ears up if you have been sort of drifting, looking at your phone or something, right? This is important. This scale needs to match what is in your histogram, so it logs the percentages accurately against each cell. So when you make your correction, it's touching the same cell with the same basis of percentage, okay? So what I can do is highlight this, and I can come over to the column axis, and I can copy the labels. Let me show you again. I want to set up my histogram. I come up here, column axis, copy labels, and I come back to my friend down here, and I want to look for the engine speed sensor, and that is not hard to find. I think it's under engine general, and you can select engine RPM right here. SAE is fine. I would take that value. No sweat. This one should be the same. But you would double click, you would add that. You make sure that your unit is in revolutions per minute. We definitely don't want to do radian seconds, right, or something like that. We want to use classic, good old-fashioned RPM. And then normally this would be empty. And because we went up and snagged that column data, I Control-V that. It slips right in, no sweat. Okay, so that's our first parameter, RPMs, speed. And again, we have to pick the parameter and set the units. Okay. We're going to do the same with manifold. So I know that my manifold is down the side here. So this is my first row, second row, third row, fourth row, right? So this time when I want to capture it, I go to my row axis, copy labels. And then I want to come back down to my tune. And this time I'm looking for the manifold absolute pressure. And this guy, I think, is an airflow manifold absolute pressure. Okay. So you grab that. It would populate here. Be sure to set your units in kilopascals. Don't use inches of mercury. Don't use pound per square inch. Use kilopascals. Why? Why would I use it? Because manifold absolute pressure on the calculator is measured in kilopascals. If you do not match those units, you will be getting false percentages and making terrible adjustments. Will not work. You must unify them, right, with units. But having said that, we do the same trick. If this was missing, right, I can come in, having copied it, there it goes. Okay. So that's how I set that up. Now that's the aggregate trims, and you'll see when we log that it's going to give us percentages across here, right? And it's going to do it in all the cells where I'm driving enough in a stable fashion that it logs, right? I have to match the condition of pressure, and I have to match the condition of engine RPM. Okay. The two together, though, I log a cell, and you'll see that these start to fill up, and I can start making adjustments. Now, what do we do about those other things I identified, though, right? The IMRC and the VCT and all that. Well, let's take them in stride here. First of all, I have an LTS-FT high, and I have a LTIFTA-SATIFTA low. Okay, we're going to look at low first. So just like before, I grab LTIFTA-SATIFTA bank separated, 2 decimals, and now we're going to add some magic. This variable, the intake manifold runner control sensor, which is out there. Let's see. If I search, nope. Oops. Who knows what we're doing now? Okay. Intake manifold, here we go. Runner control sensor. So it happened to be under engine, airflow, variable intake and displacement on demand, the intake manifold runner control sensor, right? So there it is. It's a voltage. I can grab that. Okay, none of this business, just grab it. And I can say, for this parameter, show me all the values that are less than a state of 2.0 volts. Okay, and let's add in, this one happens to be map point 14. This gets to my other thing, okay, which is this. We're going to put this away for a minute. In your parameters that you are logging of all the various channels, you really want to place them in sections where things are related to one another. So for example, I have some general stuff up top. I have some air stuff. I have all my fuel stuff in one spot. VCT stuff, right? Torque stuff. Okay, and you'll see down here I have captured mapped points 0 through 26 and the OP. Okay, when I log, it will show which mapped point is active, and that means that's the volumetric efficiency table, the speed density table that it is pulling from. Okay, so part of what you'll see in the next video is we're going to tell the tune, I want you to operate in map point 0 and map point 0 alone, and I want you to stay there. And in fact, what I'm really going to tell you is to stay in map point 10 for the high states of the IMRC and map point 0 for the low states of the IMRC. And when I set up my table over here and I go to my layout, interesting. When I go to my layout, 2 volts here, and then I have selected the map point 14, but I don't want map point 14. For the low state, what I really want, and I realize now I think I just got those backwards. I want to map point 10 because, dear viewers, I have led you astray. It's actually the IMRC low condition that's in tables 10 through 19, which is the lower power version. Okay. So that addendum aside, this still holds true. Show me all the values that are under 2 volts and show me all values where mapped point 10 as the active table is higher than 90%, because you will see in the log what will happen is it'll show that these have percentages, right? And this works, this logic, okay? And so it'll only show me in my graph here, right? I will only get values in here with trim percentages I can tune with. Oops, I was in high. With tune percentages I can calibrate with if the conditions are met. It's in the low voltage state, and it's in this particular pocket, right? And it's map point such and such that you're looking for, right? And that's the point of all these filters. So going back here, that's low, map point 10. Now if we go to high, you will see here that it's still the IMRC sensor and voltage. This time though, I'm looking for values greater than 3 volts because that is the on state for the IMRC. And because it's on and we're in the high state, if 10, map point 10 was the low state, the high state is actually map point 0. Okay. And between the two of these, I will have a full map of my speed density trims. And you'll see the two together complete a picture. That's why aggregate trims will give you the whole picture, and you'll see that this then gets split between high and low when we come back and look at the log. Okay, we're going to leave distance alone for now. If you're particularly interested and want to get ahead, this is going to measure at any single moment what the distance is from the current VCT schedule over to optimal power. That's some inside baseball. If you're excited for a bonus round, go check that out. These EQs are going to be for wide open throttle speed density tuning, because remember I said we're going to be looking at lambda error in addition to the trims for those up high states. Okay, so that's all you need to know for this guy for now. All right, so the other thing I'll remind you as I get ready to close here, because I will then show you the log in the next video and how we're going to tweak it. You're going to want to make sure you're logging your drive mode requested. Closed loop active is good to see. Definitely need your Latiftas. Later on, you're going to want to make sure you're getting your EQ ratios. Here we go. Later on with managing VCT and the camshafts, you're going to want to have your intake and exhaust cam angles. You're going to want to have your variable camshaft exhaust and intake cam angles. Right? Okay, so then these. Intake manifold runner control sensor you must have, and then this one as well. I forget what value that is. I'm not sure I can get, oh, maybe I can. Bank 2. I don't think you need bank 2. This one is the one that I usually manage against. That should be it. The one that I'm kind of hemming and hawing on is I want to make absolutely sure that I think it's drive mode. That's going to tell you, if you come over here, we're going to close you, Mr. Calculator. We're going to go to airflow. We're going to go to variable camshaft. And here you see here are our schedules, right? So logging that drive mode is what's going to tell you, are you in emission reduction? Are you in fuel economy? Were you in transient, right? Which actually you don't really see that. Were you in optimal stability, right? And then these are the actual tables themselves. So for complete logging and making sure you're running the way you were intending, it's good to make sure you're logging those as well. Okay. All right. So that's that. That's video 1 to get started, right? The next video, we're going to look at a log of my car running just in general. It's had a round of speed density tuning in the summer. It is now fall, so I wouldn't be surprised if my trims are a little off because of the crisper temperatures, right? And we're going to look at that. We're going to look to see if we've had the torque monster damping us, especially given that I went to Dark Horse torque models. And we're going to see what the map points look like, the IMRC, all that stuff, right? And then we will go through and set up a tune to begin looking at tables 0 and 10 and force the car to operate in those tables, right, or in those map points. Then we can go and gather data to calibrate them, right? And then once you see those, you do all of those tables pretty much the same way. So tables 0 through 20. Which is both the high and the low state. Then we're going to have a third video on power, right? We're going to be looking at how we calibrate for the wide open throttle power tables, right? And then with all that in hand, you have a complete speed density tune. Now, is this time consuming? You bet your ass it's time consuming. Okay, there is a lot of logging. Each table, each run of a speed density log takes anywhere from, really it should be 45 minutes, and it's usually 2 iterations. So if you think about that, if I have 26 tables and I go through 2 iterations, right, so I do a 1.0 to start, file 1.1 and then 1.2, that's 3 logs for 26 tables. That means we're going to go out and log 75 times, roughly, right? Each, half hour to 45 minutes of driving. Okay. Is it a lot? Yes. Are the tuners that you hire going through and meticulously touching each of these tables to make sure you're in good shape? No way, right? It's not commercially profitable. And that is one of the areas where the DIY home tuner who's obsessed with just their car can actually come up with a tighter calibration than the commercial guys. Now, the commercial guys know a lot more about settings elsewhere in the files, right? And especially when you come to something like forced induction, right? The guys you can hire through sites like Lethal, right? And, the actual tuners at Whipple themselves, they know how to touch all the other stuff, right? But when it comes to just good old-fashioned calibrating your tables, right, for accurate fuel delivery, which is the foundation on which all other things are built, right? This is where we have a bit of a leg up with time and effort. So next time you will see that. I will stop now. Good luck and happy tuning. All right, we just got back, and let's see, this is the tune. Here's our log. So this is a pretty good log, 46 minutes. I managed to get, excuse me, plenty of interstate time, local road time, some hills, a lot of just basic stable driving. And you can see on the bottom here, hopefully, there's a couple of spots where we gave it the beans, right? And we are going to see how we did. I have no idea. This is the first time I'm laying eyes on this. So first of all, let's see down the left here. I can see torque source. That's good. We're going to be looking at that a lot. Play with my screen a little here, whatever. It is what it is. The popcorn torque max source. Love that. You can see the IMRC was at 1.56 volts at the time of this reading. Right, this is one of many. And look, how about that? We see we're at map point 10. You will see a lot of map point 10. If you are idling, you are at 10, right, or low. 10 and 11 share most of the low throttle stuff, so they show up a lot. Okay, and then let's see. The other thing is, what drive mode was I in? Oh, I was in sport mode. Okay. All right, so that's where, you know, sport, comfort, economy, that was where I set that. I wanted to see what VCT schedule I was in. And shame on me, it looks like I don't have that. So we're going to add that before we go to the next log here. Because, yeah, I don't see it. Anyway, all right. So let's begin by looking at the long terms. Hey, okay. So from the summer tune to now, you can see that consistently I'm lean across the board here, right? Especially down low. Up top, not so much. That's a good thing, but those are probably, yeah, little itty bitty counts, right? The bulk of my data here, though, something going on. STs. This is pretty good. What you don't want to see your big numbers and swings here. So we did kind of okay. So that's the first clue. The second clue is if we'll go to our aggregate trims. Okay, so this is the real rubber meets the road. Like we saw up with the fuel trim history, we can now see by cell that there are spots where we are lean. Now look, this isn't terrible, right? Even 7, not that bad. Again, anything under 5 is pretty good, right? But clearly here, 930 counts of data, right? This idle state is lean, right? So I know now that I want to come in and touch that. Other areas, right? This is where the bulk of my data is, 1039. Okay, so we're going to have to touch on that stuff. Now, one thing to keep in mind here, right? Let's start sliding around down here a little bit, and we'll give this some room. Okay, and let's adjust our focus. Is it these? No, it's not those. What am I doing? I'm having a brain fart. There we go. All right, so let's zoom out a bit. We'll come back over here. Now, if I go down here, you can see as I move through the log, keep an eye on these mapped weights. See how it moves around and dances? So like here's a point where 13 was involved, 97%, but 2% of our calculations are coming from map point 12. Let's see. Wait, there we go. Here's an even better situation. We were at 2600 RPM, going 50 miles an hour, probably cruising, and look, half of our blend was coming from table 10, half was coming from map point 11, and its corresponding speed density table, right? So I say that because what you're seeing here in aggregate trims is across the board, all mapped points. How are we doing? And the answer is pretty good, right? I'm not too upset, but I do want to bring a few things in. And I can see here, let me back up a sec. This is kind of kaleidoscopic, and by that I mean this might be map point 10 and 11 dominant. This might be map point 13 and 14 dominant. Up here we know we're probably in map points 20 through 25, right? I know that just from experience. The point is this is all the map points operating in totality, right? And so when we want to actually zero in on a few things, I can go to, remember these histograms I created? Very interesting. So looking into this again, for low, again, I'm looking at map point 10, right? Just map point 10. Show me just those things that, and also where the IMRC is under 2 volts, right? And if I filter on that, give me the low state and map point 10, here we go. Those are lean. So what I know I can do now is go into map point 10 and start touching those up. Now I'm not going to do that till the next run, but it tells me that I have work to do on map point 10. I can change this, and first of all I could clone the table if I want, right? But I'm just going to do a quick dirty hack here and say instead of map point 10 and its speed density table, show me map point 11. And here you see our data changed a little bit. Now we're over here, right? And we see map point 11 is also a little lean. And we're going to want to touch it, right? But I bet if I go through to, let's take something like 17. And I bet I might not even have any data for map point 17. But let's find out. Nothing, right? That tells you something, right? It tells you we did not spend a lot of time in map point 17, certainly down low, which does not surprise me. And then just for funsies, let's try map point 19, which is the verge of power. Again, nothing, right? And I only got one datum there, right? And I filtered it out as noise. So you can kind of see how, that works. Now, if I was commanding it to stay in table 19, different story, right? But I wasn't. So let's go back to mapped point 10. Now that's for the low voltage state where we're cruising. High voltage state where the IMRC is open, right? We're looking at 0. And if I actually look at that table, nothing. Absolutely nothing, right? And I told you that means the ECU was not commanding it to pull from any of the drive modes looking at map point 0, and that's okay. When we command it to stay in table 10, you will find that 0 then begins populating for the high power stuff. And that is part of the fun, right? Distance tables, nothing. That's weird. Oh, 25. Huh. Oh, you know why? This is one of those ones like, why didn't I get data here? Because where over here are you mapping distance? Nowhere. So I'll have to add distance and I'll have to add drive mode. And If you ever find yourself in a situation where you've carefully constructed a histogram and yet it is not populating, why is that? Probably because you haven't included the parameter here for measuring, right? So we're not going to worry too much about that. Just for fun, let's look at MAF. You can see here we're lean low. Now, let me back up for a sec. We're looking at mass airflow, but this time, let me transition. This time, we're still using these, but our MAF adaptation is still disabled, but I have cylinder air anticipation enabled. That means the speed density based calibration model is in play, right? It's like a little machine learned sort of, it's not quite an AI, but you know, it's a predictive modeler, right? And it's based on speed density. So this time, last time with MAF, I removed this from the equation to focus on MAF. And even then, speed density was creeping in, right? We can tell. This time I'm saying, blank check to speed density. Speed density, please control all things. And so now, and it is, right? And so now when I look at the mass airflow, I'm still, though, looking at trims matched against airflow breakpoints. And it's not a surprise to see, you know, here it's breaking it out by pressure and RPM. Here it's looking at, you know, the mass airflow sensor itself. And look, the trims here again on the bottom are kind of lean. We're going to touch those. Up here up top, it looks like the modeling we did over the summer is still holding up pretty well. You know, I'm not going to complain about that. And this one as well. Now that's a good thing because I'd rather not go through all my tables right now, right? I want to show you how to do this, but I don't want to necessarily do it myself right now. But I can tell based on this that I've got cleanup work to do on tables 10 and 0 and probably 11 and 1, right? Maybe 13, who knows, right? And then depending on what watt looks like, in fact, what does watt look like? I'm not worried about that. And I'd rather not put watt miles on the car right now for the sake of cleaning that up. That looks pretty clean. That's a little sketchy, but again, it's under 5. And then this one's clean as a whistle, right? And if you look at my filters, EQ, lambda. So for lambda, what I'm saying here is only show me data where the commanded lambda is under 0.86, which corresponds with when we're wide open. So there you go. Now the only other thing we want to look at while we're here, well, 2 things actually. 1, knock retard. Did we at any point get significant KR? And you can see down here I'm mapping this in red, but I'm just kind of eyeball it. There we got a little bit, -1.2, no big deal. 0.9, nothing to write home about. Here we are going through some power, and this is where I'm going to actually zoom in a little bit. We're going through some power. Here's a spot. Where's that 3.3? There we go. Interesting. So we were at 1694, 11 miles an hour. I think I was probably hitting it a little bit. And it had 3.3 degrees of knock. I wonder why. That's not crazy, but interesting. Probably noise. Here, under some throttle, no big deal. Check over on some of these. You know, I'm not seeing anything to write home about. That's good. So we're not running too hot. We're not unstable. We're not producing detonation. Okay. And so then, torque. Torque source and torque max source. Okay. So for these, again, looking at some of our power stuff, idle speed, oscillation, decel fuel cut. So there I was decelerating, so that's where I was getting it from. That's all good. Idle speed. Torque max source is still the, what's the supercharger load limit? That's pretty cool. Fuel cut, driver demand, oscillation. The tip-in limit, that's fine. I'm not seeing any sort of danger-based limiting of torque. Let's look at something where we're going. There we go. So yeah, let's come up here. Through this range where we're hitting 6,000 RPM, torque source the whole time, under throttle, driver demand. That's good. That's very good. That means we weren't hitting limits. This one, the oscillator. But as we're hitting the power, it looks good. Any other big driver demand? Okay, that looks good. And we're going to talk more about this when we get to the actual torque method. And I'm going to look up more about oscillation. And I wonder if that is the same as something else I was looking at. Yep, the anti-shuffle. Okay. So anti-shuffle helps balance things if you've got a wiggly foot on the pedal. It just helps smooth out low-end acceleration. It's not a bad thing. And you see here for the most part where I'm really hitting it though, again, all driver demand. Oscillation, because we're bouncing around a little, driver demand. It's exactly what I want to see. So it looks like the Dark Horse torque is working, which I would have thought, because all we did was increase our torque ceiling, which, by the way, there's multiple ways to do that, but that's not the point of this video. So for there, we're going to stop. Next time we'll get into how we're going to clean this up, and from there, how to go to power, and on we go. So very good. See you in the next video, and happy tuning.